Alright, welcome to the last lecture for Test 4. And first of all, don't freak out when you see these graphs on here because this is just an illustration. What we're going to do isn't this bad. We're going to look at solving quadratic nonlinear inequalities. And the last one we look at will actually be a cubic. But just to give us an example of what we're going to be doing, remember, one, if it's a polynomial of degree 2, then that means it's quadratic, which means that visually it's a parabola. And you may remember in a previous lesson, I told you that when we solve quadratic equations or functions, that we're finding the zeros, which are the x-intercepts, or where that graph crosses the x-axis. So what these are illustrations of is each one of these is a parabola, and you see that the parabola crosses in each one of these cases the x-axis at two places, and those are going to be the end points because there are zeros when we look at this type of problem. And you see that it creates regions. We have this region that is on this side of that endpoint. We have one that is between these two endpoints, and then we have one that's to the right of the endpoint, and that's true of each of these graphs. So depending on what the inequality is that we're looking for, the shaded part here is representing solutions that the numbers, any that we pick inside that shaded region, would make our inequality true. So let's work an actual problem. So this says solve the nonlinear inequality and give the answer in both graph and interval form. So this is my nonlinear inequality. You notice it is quadratic because I have an x times an x will give me an x squared. And we already know from stuff that we've done previously, if I have this binomial times a binomial, and for our sakes here, we're just going to say equals 0, that we can solve or find those two endpoints, by setting each one of these equal to 0. This isn't different from what we've done before. So this is a number line, and what it represents is the x-axis that's in these pictures. Okay? So you can kind of picture that there is a parabola coming down, and it's crossing the x-axis here and here. And those two numbers are x equals -4 and x equals to 6. Now in this case, when I solved these, the smaller number happened to be on the left. But remember, because this is a number line, whatever you get for your endpoints here, they have to go onto your number line in numerical order from smallest to biggest, okay? So this has created, like we talked about above, 1, 2, 3 regions. All right? So we want to know if the numbers in region 1 make the inequality true, if the numbers in region 2 make the inequality true, and if the numbers in region 3 make the inequality true. So you've probably done this before with linear equations, linear inequalities. anytime we want to know if something is a solution, then we plug it into the given equation or inequality and see if it's true or not. Because if it gives something that's true, then that means it satisfies that equation or inequality, so it is a solution. So what we're going to do is choose a value in each one of these three regions, and we're going to test it by plugging it in to see if it gives me true statement or false statement. So what we need is a value that is representative of each region. So this first thing says test interval. So when you see interval, we've talked about interval notation previously, right? So I want the interval first that describes from here to here. That's my first region, right? So remember when we're talking about interval notation, if I have an arrow, then that means it's continuing forever, so we're going to be talking about an infinity. So if the arrow points left, it's a negative infinity, and if it points out to the right, it's positive infinity. So this test interval, we always read them from left to right. It begins at an arrow pointing left, so it begins at negative infinity, and it continues until we get to our endpoint, negative 4. And we're not going to look at the inequality here. The test interval, this is always going to be a parenthesis because we're going to look at the endpoints at the end. So all we want to know is what interval can we choose our number to test, all right? So region 2, it begins at that endpoint negative 4, and it goes to the endpoint 6, and then the third region begins at 6 and goes out to an arrow pointing right, which is infinity. So the value that we choose to test, it just has to be in that interval. So for instance, to test region 1, I just need an x value that is smaller than x equals negative 4. So just be careful with the negatives because it can be confusing sometimes. Picture your number line in your head if you need to. So as we go further away from 0, remember those numbers get larger in absolute value. So you can pick any number that is to the left of negative 4. I'm going to pick x equals negative 7. You could have chosen negative 5, negative 10, negative 50. I'm just choosing negative 7 because it's a representative point in that region. Okay? So then to test it, that's what the work is. We're going to show the work to test this region to see if these points give me true statements and are solutions. So my inequality is x plus 4, x minus 6 bigger than or equal to 0. So I'm going to substitute negative 7 for both of these x's. And we're just going to see if this is true or not. So negative 7 plus 4 is negative 3. Negative 7 minus 6 is negative 13. And if we multiply negative 3 times negative 13, we get 39 bigger than or equal to 0. So then we want to know, is that statement true or false? And 39 is certainly bigger than 0. So we get true. And what that means is x equals negative 7 made our inequality true. So it is a solution. And of course, we can generalize then and say that because it's a representative of that region, that any number in that region is going to be a solution. So graphically, we represent solutions by shading them. Okay? Now, I did not put a parenthesis or a bracket at that end point yet. We're going to come back to that once we finish with this part, okay? All right, so for regions 2 and 3, we're just going to repeat this process. In the middle here, I need an x value to test that's in between x equals -4 and x equals to 6. Well, you know, math people generally tend, anytime 0 is available, we like to test it because it makes the math pretty easy most of the time. And 0 is between -4 and 6. So I'm going to use 0 in this region. So then to test it, we have 0 plus 4, 0 minus 6, and we want to know if that gives me something bigger than or equal to 0. So I get 4 times -6 is bigger than or equal to 0, and that's -24 bigger than or equal to 0, and a negative number is not bigger than or equal to 0. So this is a false statement. So the numbers in this middle section are not solutions to my inequality. So we're not going to shade anything between -4 and 6. All right, so we got one more region. So we need a value this time that is larger than 6. And again, you can pick any number to test that's bigger than 6. I chose to use 8. You can use 7, 15, 150, anything that's bigger than 6. Okay? Then we're going to plug it in to our inequality and see if we get a true or false statement. So 8 plus 4 is 12. 8 minus 6 is 2, and I get 24 bigger than or equal to 0, and that is true. So that means that the numbers larger than 6 are also solutions to our inequality. So I'm going to shade in this portion as well. All right, so the last thing we need to do then is look at the endpoints themselves. So our endpoints are x equals -4 and x equals to 6. So we need to know whether we're going to use parentheses or whether we're going to use brackets. And this is where the inequality symbol comes into play. Our inequality symbol is bigger than or equal to. If we have an equal to, then that means that the endpoints will have brackets. An inequality by itself with no equal would be parenthesis. So I'm going to go up here to my graph, and at my endpoints, I'm going to use a bracket that faces my shaded region, and the same for here. So at this point, that is my completed graph. So it asked me to give the answer in graph and interval form. So that's the graph, it's completed. So my interval answer, I'm just going to write the intervals that describe those two regions that we shaded. So the first one, just like from here, right? It started at -infinity and it went to -4. But now that we've tested the endpoint, we know that this is a bracket. And if you remember from linear inequalities, if we have a gap like we do here in the middle, anything between -4 and 6 is not a solution, so we have a gap there. Then we use a U to combine those two disjoint sets. So the solutions start again at the endpoint 6 with the bracket and goes out to infinity, so it's positive infinity. So this is the answer for the interval notation. Now I do want to make one note. Don't try to memorize patterns. When we did linear inequalities, they were a little simpler, that we could say if it is a less than, it was going to shade to the left, and if it was a greater than, it would shade to the right. That works just fine for linear inequalities, but once we get to quadratic and higher, we do have to test each region. We cannot make assumptions from the original problem about which regions are going to be solutions. So you do have to show this whole process and test each region, okay? So when it's not linear, the inequality sign itself does not determine where we shade for solutions. That it does indeed take this entire process. All right. Let's look at another one. The basic difference with this one is this time the quadratic is given to me in standard form. It's not already factored. So that means we have to do the factoring step first. So this one, I believe, is indeed factorable. I probably would not, give you one that had to be solved with the quadratic formula, because of course that would probably lead to complex or irrational answers that we would have to test and worry about. So you probably aren't going to have to worry about that. They should factor. So I have an A of 1, so we know these have to be X. And then for my factors of 12, we have 12 and 1, 3 and 4, 6 and 2, and I think it's going to be 6 and 2 to give me the 4, right? So I'm going to put a 6 and a 2. And the 4 needs to be negative, so we need -6 and +2. So now this problem is in the same format as the last one we did, so it's going to work exactly the same from here. I'm going to set each one of those factors equal to 0 so we can find our two endpoints. So I get x equals 6 and x equals -2. So don't forget what I told you in the last problem. Regardless of what order these come out when you solve, this is a number line. So we have to put them on here from smallest to biggest. So we have x equals -2 and then x equals to 6. All right. So my intervals, the first one is going to start at that arrow on the left, and it goes to the endpoint at -2. The middle region is -2 to the next endpoint of 6. And then the last region starts at 6 and goes out to positive infinity. So we just need to choose a test value in each one of these regions. So first we need any number that is to the left of -2. I chose -4. But again, you can choose any number, -3, -10, -70, whatever you want. And then you can put it into the original. I will agree that that's safer. The math is simpler to do if it's in its factored form. So one, if you do this, make sure that you've factored carefully and correctly. But I'm going to use the factored form to do my testing, just because you see the math is going to be a lot simpler this way, right, than plugging it in to the original with the squared into 3 terms. So this gives me -10 times -2. That gives me 20. And 20 is not less than 0. So that means we got a false statement, and these numbers are not solutions. So we're not going to shade anything on the number line for that section. For the middle, it's something between -2 and 6. So anytime 0 is available, I'm going to use that. If I plug in 0, I get -6 times 2, -12 less than 0. -12 is less than 0. So numbers in this region give me true statements, and that means they are solutions. So we're going to shade in between the -2 and 6. And then for my last region, I can choose anything bigger than 6. So I chose 8. But again, you can pick anything that's bigger than 6. So if I plug that in, I get 8 minus 6. 8 plus 2 less than 0. This is 2 times 10 less than 0. 20 is not less than 0. So this is false. So I'll make one statement here. You've probably started to notice a pattern. In the last problem, if you note, we got true, false, true, so they alternated, right? And if you look here, we get false, true, false. So while you cannot use the inequality sign at the beginning to determine what your solutions will be, one thing we can look for is the regions should alternate. You should not get the same conclusion for 2 of these regions in a row. So you shouldn't get false, false, true, or true, true, false. That shouldn't happen. They should alternate. If they don't, you probably need to check your work. Okay? So now the last thing we need to do is check our endpoints. So x equals -2 and x equals 6. So our inequality sign this time is just a less than. There's no equal. So that means that we're going to use parentheses for our endpoints. So I shaded this middle region. So at my endpoints, we want parentheses that each face that shaded region. And then the last part is to write the answer in interval notation. So the solutions are the numbers in between -2 and 6. And we write that interval parenthesis -2, 6 parenthesis. Okay? One more. Of course, the only difference with this one is you notice I have 3 binomials being multiplied. So this one isn't a quadratic, it's not a parabola, this one is a cubic. But we're going to work it the same way. It's just that we're going to have 3 endpoints, so we have 4 regions, okay? We're still going to set each one equal to 0 to determine our endpoints. So I get -2, 3, and 5. And those are in numerical order. So the first one is -2, the second one is 3, and the third one is 5. So my first test interval, of course, begins at my arrow pointing left, and it goes to the first endpoint. The second interval begins at the -2 and goes to the next endpoint of 3. And then the third region starts at 3 and goes to 5. And then finally the last one is 5 to infinity. So of course we have to choose 4 test values this time. So the first one is anything to the left of -2. So I chose -4. You can choose anything that's in that region. So we're going to put the -4 back into our original inequality. And we want to see if it's true, just like before. So this gives me -2, -7, -9. And at this point, I used the calculator and did -2 times -7 times -9. And hopefully I got the right number. -26 bigger than 0. That negative number is not bigger than 0. So I get false. So that means we're not going to shade in that region. Those are not solutions. Between -2 and 3, 0's in there, so I'm going to use 0 when I can. So if I plug that in, 0 plus 2, 0 minus 3, 0 minus 5, I get 2 times -3 times -5. Again, I use the calculator for this part. So 2 times -3 times -5, I got 30 bigger than 0. And this one is true. So that means we're going to shade that region because those are solutions. Now between 3 and 5, you actually have an infinite number of choices, although it looks like you don't. But if you're like me, I'm going to choose the integer. You could choose 3.1, 3.5, 3.7, 4.2, but I'm going to make it easy on myself and pick 4. So if I plug that in, I get 4 plus 2, 4 minus 3, 4 minus 5. So this is 6 times 1 times -1. And if we multiply, we get -6. That is not bigger than 0. And from what I told you, that's what we were expecting, right? I have false, true, so I'd be expecting this one to be false. And I'm going to be expecting this one to be true. But don't skip and don't show the work, okay? So for the last region, I want something bigger than 5. So I chose 7. Of course, you can choose any number that's over there. So if I plug in 7 plus 2, 7 minus 3, 7 minus 5, then I get 9 times 4 times 2. And if I multiply that out, I think I got 72. That is bigger than 0, so we got true like we were expecting. So we're also going to shade the region that is bigger than 5. And then the last thing is my endpoints. So we have 3 of them. X is -2, X is 3, and X is 5. My inequality is a greater than with no equal. So we're looking at parentheses. So if I go back to my graph, I'm going to enclose the second region with parentheses. And then the third region, we want everything to the right of 5. So finally, my interval notation. We're going to have a union again because we have two disjoint sets. From the left, our first region begins at -2 and goes to 3. Then we have our gap. It starts again at 5 and goes to positive infinity.